Student, I am going to talk to you about mass spectrometry part first. In this part, I will discuss introduction, principle, and some ion sources of mass spectrometry. Mass spectrometry is not a form of spectroscopy because it does not involve the absorption or emission of electromagnetic radiation. Mass spectrometry provides information about the elemental composition of sample, the structure of inorganic, organic and biological molecule, the qualitative and quantitative composition of complex mixtures, the structure and composition of solid surfaces, the isotopic ratio of atom in sample and the accurate molecular weight of sample. Here is the introduction. Mass spectrometry uses high energy electrons to break a molecule into fragments. Separation and analysis of the fragments provide information about molecular weight and structure. The impact of a stream of high energy electrons causes the molecules to lose an electron, forming a radical cation, a species with a positive charge and one unpaired electron. The impact of a stream of high energy electron can also break the molecule or the radical cation into fragments, and the ions are separated in the mass spectrometer according to their mass to charge ratio and are detected in proportion to their abundance. A mass spectrum of the molecule is thus produced. It displays the result in the form of a plot of ion abundance versus mass to charge ratio. Ions provide information concerning the nature and the structure of their precursor molecule. In the spectrum of a pure compound, the molecular ion, if present, appear at the highest value of M/Z, followed by ion containing heavier isotopes and gives the molecular mass of the compound. Here is the background of mass spectrometry. Demonstrate the canal ray can be deflected using strong electric and magnetic field, which is discovered by Wilhelm Wien in 1898, and measure the mass to charge ratio of electron, and begins his study of positive rays by J.J. Thomson in 1998 and 1905. The first electron impact source, solid, by Arthur J. Dempster in 1918, and the first electron impact source, gases, by Walker Blackney in 1929, TOF mass analyzer by William Stephens in 1946, quadrupole mass filter and quadrupole ion trap by Wolfgang Paul 1953, and chemical ionization by F.H. Field in 1966, field desorption ionization by H.D. Baquet in 1969, and 252 CF plasma desorption by McFarlane and D.F. Torgerson in 1976, triple quadrupole mass analyzer by R.A. Yost and C.G. Young in 1978, and FAB by Michael Barber in 1981. Here is some Nobel laureate. They received Nobel Prize in the field of mass spectrometry. In 1906, Nobel Prize for Physics won by J.J. Thomson in recognition of the great merits of his theoretical and experimental investigation on the conduction of electricity by gases. Francis William Marston in 1922, Nobel Prize for Chemistry for his discovery by means of his mass spectrograph of isotopes in a large number of non-radioactive elements, and for his enunciation of the whole number rule. In 1989, Nobel Prize for Physics won by Wolfgang Paul for the development of the ion trap technique. John Van Fen, 2002, Nobel Prize for Chemistry for the development of soft desorption ionization method by mass spectrometric analysis of biological macromolecules. In 2002, Nobel Prize for Chemistry goes to Kochi Tanaka for the development of soft desorption ionization methods, MALDI, for mass spectrometric analysis of biological macromolecules. Here is the basic principle. A mass spectrometer generates multiple ions from the sample under investigation. It then separates them according to their specific mass to charge ratio M/Z and then records the relative abundance of each ion type. The first step in the mass spectrometric analysis of compound is the production of gas phase ions of the compound, basically by electron ionization. This molecular ion undergo fragmentation. Each primary product ion derived from the molecular ion in turn undergo fragmentation and so on. Here is the representation of molecular ion formation and their fragmentation and rearrangement followed by fragmentation and collision followed by fragmentation. All these are depicted in this diagram. Instrumentation, the inlet system transfer the gaseous form of sample into the vacuum of the ion generation chamber of mass spectrometer. In the ion generation chamber, neutral sample molecules are ionized and then accelerated into the mass analyzer tube. The mass analyzer tube is the most important part on which a range of the mass spectrometer depends. This segment separates generated ion either in space or in time according to their mass to charge ratio M/Z. Once the ions are separated, they are collected and detected in ion collector chamber. Then the signal is transferred to a data collection system for data investigation. The high vacuum is applied between the ion generation chamber, analyzer tube and ion collector. The vacuum system is maintaining the low pressure which minimizes the chances of ion molecule reaction, scattering and neutralization of the ions. Here is the representation of mass spectrometer. Here is the sample injection port where we inject sample. Here is the source, ionization source you call it, and next is dispersion system, and next is detector, and where we get signal to convert into a mass spectrogram. Inlet systems. The purpose of the inlet system is to permit introduction of a representative sample into the ion source with minimal loss of vacuum. Most modern mass spectrometers are equipped with several types of inlets to accommodate various kinds of samples. The system must be able to vaporize molecules of low vapor pressure such as high molecular weight organic and organometallic compounds. The inlet operate at low vapor pressure 10 to the power minus 4 to 10 to the power minus 7 torr and high temperature up to 300 degrees centigrade. This system must be leak tight. High temperature vacuum system and batch inlet system is the most common one. First, ionization source. The ionization source is considered to be the heart of the mass spectrometer. In the ion sources, the analyzed sample are ionized prior to analysis in the mass spectrometer. A variety of ionization techniques are used for mass spectrometry, and the most important consideration are the internal energy transferred during the ionization process and the physicochemical properties of the analyte that can be ionized. Some ionization techniques are very energetic and cause extensive fragmentation. Other techniques are softer and only produce ions of the molecular species. Electron ionization and chemical ionization are only suitable for gas phase ionization, and thus their use is limited to compounds sufficiently volatile and thermally stable. However, a large number of compounds are thermally labile or do not have sufficient vapor pressure. Molecules of these compounds must be directly extracted from the condensed to the gas phase. These direct ion sources exist under two types: liquid phase ion source, electrospray ionization, atmospheric pressure, photoionization. Fast atom bombardment uses N in volatile liquid matrix. And solid state ion sources, matrix assisted laser desorption ionization, secondary ion mass spectrometry, plasma desorption, and field desorption sources all use this strategy to produce ions. First ion source is electron impact ionization. For its most popular model, the electron impact ionization with magnetic sector analyzer, the sample under investigation is converted into vapor phase and bombarded with electrons having energy sufficient to knock out one electron from it, greater than 10 electron volt, to produce a positively charged ion called molecular ion or parent ion. The lifetime is greater than 10 to the power minus 5 second. The energy imparted to the molecule by the impact of the ionizing electrons is usually greater than the ionization energy. Excess energy may remain in the molecular ion, making the molecular ion very unstable. Generally, these energies can be used to break one or more bonds of the molecular ion. Depending on the energy available, molecular ion may remain or dissociate either by eliminating a radical or by losing an even electron molecule. Ion formed are separated in analyzer under the influence of electric and magnetic field and are recorded by the detector to give rise a mass spectrum. Here is the representation again, molecular ion and molecular ion again undergo fragmentation to form a even ion and radical, and again it will also fragment into odd ion and a neutral molecule. The extent to which the molecular ion fragment is usually relatively large when electron impact ionization is employed. Sometimes it is impossible to detect an appreciable abundance of the molecular ion. This problem is a serious drawback of electron impact ionization. In some cases, it is possible to increase the relative abundance of the molecular ion by reducing the energy of the ionizing beam of electrons. When the energy of the ionizing electrons approaches the ionization energy of the molecule, the excess energy remaining in the molecular ion is small and fragmentation is decreased. However, the large degree of fragmentation associated with electron impact ionization is often advantageous. Next is chemical ionization. Chemical ionization is a technique that produces ion with little excess energy. Thus, this technique presents the advantage of yielding a spectrum with less fragmentation in which the molecular species is easily recognized. Consequently, chemical ionization is complementary to electron ionization. Positive chemical ionization uses methane, isobutane, or ammonia as reagent gases. Negative chemical ionization uses methane reagent gas in electron capture mode. A reactant gas is introduced into the ionization chamber, whose molecules become ionized on collision with a beam of electrons accelerated by a 400 volt potential difference. Plasma formed is driven to the center of the source by electrostatic lances. Ionized reagent gas protonate the sample molecules, leaving a neutral reagent gas species. The molecular ion is a pseudomolecular ion peak at M+1 with weak internal energy and little potential for fragmentation. Therefore, molecular weight is easily determined, and its fragments provide information on the molecular structure. Here is the primary ion, methane, undergo molecular ion and again fragmentation to form a cation, and this cation again transfer its charge to sample and to form a molecular ion. The main problem with the classical chemical ionization technique are still the need for the analyte to be in the gas phase and the high pressure condition under which chemical ionization must take place. The latter condition may lead to high accelerating voltage discharge in the ion source. Next one is fast atom bombardment ionization, FAB, used for large compounds with low volatility, for example, peptides, proteins, carbohydrates. Solid or liquid sample is mixed with a non-volatile matrix, for example, glycerol, crown ethers, thioglycerol, meta-nitrobenzyl alcohol. Immobilized matrix is bombarded with a fast beam of argon or xenon atoms. Argon molecules are introduced into the reduced pressure chamber where they are ionized by the ionization source. The ion formed are pulsed towards the collision chamber and they exchange their charge with the neutral molecule organ. And here is the exchange of charge of organ molecule. By exchanging the charge, the ions become neutral, but they still have enough kinetic energy and they pass the electrostatic gates which have the effect of eliminating ions that have not yet exchanged their charges. The fast atoms are directed at a target that contain the samples. The bombardment of atom does not create ions, it only extracts ion from the surface. Charged sample ion are ejected from the matrix and extracted into the mass analyzer, gives positive M plus MH plus and a negative MH negative pseudomolecular ion. Another ion source is matrix assisted laser desorption ionization, MALDI. MALDI make use of absorption of laser light by a solid sample layer. The energy uptake upon laser irradiation then causes evaporation and ionization of the sample. MALDI method use a solid aromatic matrix, for example, acids such as alpha cyanocinamic acid, synapinic acid, 3,5-dimethoxy-4-hydroxycinamic acid, picolinic acid, 3-amino-picolinic acid, etc., where the sample is dispersed in a definite proportion, one sample molecule per 10 to the power 4 matrix molecules, both in crystalline state and at room temperature and atmospheric pressure in dry nitrogen atmosphere. Laser irradiance is a critical parameter in MALDI. A variable beam attenuator in the laser optical path is employed to adjust the irradiance, for example, by means of a rotating UV filter of variable transmittance from close to 100% down to about 1%. Then the laser attenuation is individually optimized for each measurement. MALDI ion sources are generally operated at ambient temperature by means of a microscope, a 3 to 10 nanosecond pulse UV laser irradiation, while those of IR laser are in the range of 6 to 200 nanosecond is focused on a small matrix spot 0.05 to 0.2 mm in diameter. Salt pulses are needed to effect sudden ablation of the sample layer. In addition, an extremely short time interval of ion generation basically avoid thermal degradation of the analyte. On the other hand, longer irradiation would simply cause heating of the bulk material. An electronic and thermal excitation of molecules in the sample matrix occurs, able to yield protons causing ionization. The matrix serves as an energy vector between the laser beam and the molecules of the analyzed compound. Ionization of organic molecule is mild, resulting in pseudomolecular ions. MALDI is the most used analytical method in modern biochemistry and polymer science. Here is the how to molecular ion formed and how they form MH negative and M plus H positive molecular ion. Thank you very much.